So good morning still, and my name is Raghavendra Selvan, but then the concise version is bolded. It's Raghav. I think that might be easier. So I'm gonna, let's see if we can talk about this concept of pattern recognition, and I think the subtitle is something I hope you'll find interesting. I'm saying thinking like machines and then vice versa. So let's see what we are trying to do with that. So before I start off, what I want to do is start with a video. Have you seen this guy? I'm having some technical difficulties here. Lights off, please. Yes. So that was. Had any of you seen that video before? No. Okay. That's not science fiction. So the robot is not as cool as you would see in the movies. It's science. So that's like state-of-the-art humanoid robots by a company called Boston Dynamics, which was also at some point acquired by Google for some point. But anyways, but then there's like one simple thing there, right? It's a task of picking up a box and then moving, and then not getting annoyed when somebody is disturbing you, right? So that's a very basic human task, but then it's actually a scientific feat that the robot is able to do that now. So now, what I'm trying to arrive at is like some things which seem very obvious, intuitive for us to do, are like hard for computers to, or robots to kind of do. So to help maybe appreciate that, let's see what are the key attributes of human intelligence. So I have put some of the points here. You might agree, disagree, or I think these are basic key aspects which describe human intelligence: logic, reasoning that we can learn from, doing self-awareness that we can, and then emotion, creativity, and also pattern recognition, right? So our brain is actually a pattern recognition engine. So you can look at something and then see patterns. You can look at clouds and then imagine, everything. We can look at stars and then think of, beautiful patterns. So I think that's an important key aspect of human intelligence. So now, as if today, so what are the key attributes of artificial intelligence? So let's see how far we've taken, artificial intelligence. Logic and problem solving, I think we're pretty much there, right? There are problems which we cannot solve, but we actually give it to the computers to solve now. Learning, do you think computers can learn? They do, right? Like your Google's prompts or the customized advertisements that you get, so I mean your Facebook friend suggestions, so the computer is learning. Self-awareness, this I've put like, maybe. So if I can reduce the description of self-awareness to being aware about yourself in your surroundings, maybe yes. Heard of Tesla, right? So it is aware of its self, right? And then it's not in the way that we think of consciousness, etc. But then with respect to your environment, the computers are. Creativity, actually yes. So if you haven't, there's also like there's something called as deep learning now, where computers are dreaming up paintings and stuff like that. So you should go search, and then you'll see like some magnificent Van Gogh-esque, paintings and things like that. So I put a cross mark here because emotions, as yet, we have no computers that can emote. So let's see if we can, take that further. Pattern recognition. So can computers recognize patterns? And that's where I put a question mark, and that's the problem we are going to solve. See if computers can recognize patterns. Okay? So before that, let's see if you can recognize patterns. So I'm going to give you like 10 seconds and then spontaneously look at this picture, and then do you see any patterns? I don't mean connect the dots, but then is there like some inherent pattern with this date? What is it?
Positive correlation. And kind of 2 clusters as well.
Okay. Did anybody else also see that there's 2 clusters here, right? So the first thing that comes to your mind is like, oh, there's a bunch of points. You don't have to think about the data or anything. There's like 2 clusters here. So now we can do it like even without putting like deep thought into it, right? So now, can we teach this task of clustering to computers? So now that's the problem. We'll try and see if we can solve through this lecture. Okay, now, before I don't stumble on the chair, here are my learning objectives. So let us see if by the end of this lecture, I hope we will be able to judge.
Just push to the window.
Yes. Okay. Yeah, that's annoying, but hopefully much. Okay, let me come back to the learning objectives. So we were trying to tackle the problem of if we can teach computers to recognize or clusters, right? So the learning objectives would be first, judge if the computers can perform pattern recognition using clustering as an example. So that's going to be one. Hopefully by the end of it you will have an answer to that. And then analyze a state-of-the-art clustering algorithm. So we'll see if it's state-of-the-art or not. And also here I've put like a fuzzy kind of a learning objective. Let's see if we can do this. Decide if the algorithm that we're going to describe is applicable to other problems also. So let's begin. Yes. Now, I want you to spend some time thinking about how your brain detected that there were 2 clusters, and then use that idea to kind of come up with an algorithm which you could make the computer to also learn. But then because computers cannot be spoken to or they don't have intuition, I'll give you a hint that you might have to think in terms of mathematics. So I'm going to give you 3 minutes, and then I see that there's like choose. So hopefully you'll have a discussion, and then think about an algorithm, how you would teach the computer to detect these 2 clusters.
So.
Yeah. So
I'm taking something very about the distance between points. So of course some
I guess it's actually us that makes it.
So just to interrupt here, just a minute. I've also put this comment that you can assume that the computer can be told that there's only 2 clusters. So you have to just find out those 2 clusters, which are the points belonging to those clusters to make it easier. So there's 2 clusters, which of the points belong to these clusters? So how do you tell the computer to do this?
Maybe that
So first you need to identify what is
What's the fine cluster?
But how should you know that above 2 or 3 that is a new cluster? So there must be something about the distances, right? So something about the narrow there.
And if we step back and actually think about like the brain of the computer, it's identifying. There are 2 separate identity here. And to know that the end of those identities
Could it be a direct shot?
each dot corresponds to a pattern.
Yeah.
Okay, so I think I'm going to stop here now and see if we have any good ideas. So can we stop at this point? So any ideas as to how you would teach the computer the algorithm to do it? Yeah?
Well, something about the distance between points.
Something about distance between the points, yes?
Pairwise distance.
Pairwise, yes. So we're going to use, let's see if, so the notion of distance between pairwise points, yes? And any other ideas?
We said the computer has to basically identify what is a cluster, what defines a cluster, so some kind of threshold of a degree of partitioning or grouping of two things or three things, you need some kind of variables to work on.
So what defines a cluster? So how does the computer know that what is the notion of a cluster? Yeah. And then do you have anything apart from these?
Can you also, in the definition, define how many points to make a cluster?
How many points?
So like, if an outlier, should that be treated as part of a cluster or as an outlier?
Okay. How many points in a cluster? Right. Yeah.
I'm not sure whether this is all within this, but we talk about like the axis. So if you are high on both axes, you are more likely to see something
So
that into it.
Okay. Use the axis, information. Okay. So I think we have some very good ideas here. So yeah, I think we've basically, if we try to kind of decompose how the brain kind of thinks, at least this is the way I kind of recognize maybe. So of course, there is a notion that implicitly you are looking for points that are close to each other, right? Like your brain is, I think, implicitly computing the distance, like, oh, this point is closer, these are all close together, that's a cluster. But then it also does something that, oh, this is a separate cluster, these are two separate clusters. So there's also a notion of, distance between clusters, right? And I think the idea is that that distance between clusters can be kind of synthesized into something like a center of mass or a centroid. So, right, if you kind of forget about the points, and then if you can somehow reduce these into center of masses, or if they start looking for centroids, then there is a centroid here, and then there is a centroid here, right? So, and then you know that, oh, there are two clear clusters. So, I think we're going to use all of these ideas, and then this notion of centroids to try and teach the computer. So, let's start. So what we basically do is like, because we know that there are two clusters, so we're looking for two centroids, but then we don't know where the centroids are. Okay, so we first randomly place them somewhere. So I don't know if you can see the color, but then it's supposed to be red and this is blue. All right, so nice. So then what we do is like, we take each point and then check which is it is closest to, which of the centroids is it closest to. For instance, we look at this point and then check the distance between this cluster and then this cluster, centroid. Which one do you think it is closer to?
Blue.
To the blue one. Yes, again, this has changed to blue. So now let's look at this point. Is it closer to this one or this one? The red or the blue cluster?
Red.
To the red one. So that has turned red. So now we do this for every point, and then we first get this kind of labeling we say. So you have like 1, 2, 3, 4 of these points are closer to this centroid, and then these points are closer to the blue one. Okay? So now, next what we do is, this was randomly placed centroids. Now we recompute the centroids using, all the points that are red, and then all the points that are, we remove these centroids. Okay? And then we recompute this new centroids. So we look at these points, and then all the blue points, and then recompute the centroids. So we get something like this now, because you see, the center of mass for all these points is here, and then for all of these, it ends up being here. Now we again do the same thing, all right? But then something interesting would happen. Previously this was blue, and it was closer to this centroid, but you can already see that it's now closer to the red one, yes? And then we actually change everything, but then some labels don't change. So now what happens is, those two blue points became red. And then we recompute the centroids of these points again. And then we try to change the labels. Now it doesn't change. So now the computer has basically, understood the notion of clusters. So this is called as K-means clustering algorithm. It's quite old, but it's still state of the art. And I'm going to try and sell it to you as to why it's also like super cool. So here the K is basically the number of clusters. So you need to tell the algorithm how many clusters you're looking for, then it will cluster your data. It's very simple as you see, but very powerful, right? And maybe you will not appreciate as yet why is it powerful, but then maybe look at it. It belongs to something, it's the holy grail for computer scientists. We call it unsupervised learning. Maybe, if you're curious, you can read up about it. So it's one of those very basic but then elegant algorithms which can learn things without any supervision. And yeah, there are of course things which make it do faster, and then adaptations to it. It's a pretty standard algorithm. So I thought you might not be impressed because we started with like a few points, right? So this is actually 100,000 data points, and then we're looking for like a few clusters, and then it's just using k-means clustering, and then you can get a cluster like this, but this is just more like a synthetic data where we just wanted to I wanted to impress you with the number of data points. So, but then there's also like other applications. So now, for instance, this is really bad here, but anyways, this was a slide. Yeah, okay, but also I think there's some resolution issues. But then this actually said it was, I think, the petal length, and then the sepal length, and then the length of the flower. So different attributes of a flower which are measured and then tabulated. And then you put them on like a 3-dimensional space now. And then you don't know, because you did not initially know which flowers you mentioned. Somebody else gave you, these data points. Then you try and cluster, and then after you perform this clustering, so then you actually can get like 3 different clusters. When you go back and then see those correspond to 3 different, flowers. So now you can start thinking about, we always deal with a lot of data, and then it's always nice to see clusters. And then what does that cluster mean? So now you could have like drug trials or whatever your domain, but then if you have like 1 million data points, see, it's very easy when it is in 2D or 3D that we can actually draw a circle around and then say, oh, this is one cluster. But then you could also add another attribute, 4D or 5D or 1,000 dimensions, and then we cannot imagine that. But the computer can still do the same clustering on all those dimensions. So I think that's why k-means is still like so powerful. Search engines, for instance, they use like Google. Whenever you search for something, you get these tabs called web results, image results, videos, and everything. So it crawls through the web, and then it clusters those results, and then puts it as these different search results for you. Social networks. At some point, I think so Facebook was experimenting with the social graph. I don't know if you can still do it. But then you could like go in and check your own social graph, and then see that it would have clusters like, oh, is this your friend circle? Is this your family circle? Is this your professional network? Are these your buddies or whatever? So those are all based on, it reads all your posts and then looks for some features which are you can segregate based on and then stock markets, of course, you can do a lot of those things. Medical image analysis. I my PhD is on that, so I use it. Silas, who sits in the room there with us, he's also a colleague of mine, and his PhD is basically about clustering. So it's still state of the art, and he uses k-means for one of his experiments. Pharmacy, anywhere you get big data, you can do k-means, and then like I said, it's simple, but then you can gain a lot from it. So, as a conclusion, I hope we assessed if pattern recognition capabilities exist in computers. So I don't know, I hope you have an answer. Like, do you think computers recognize clusters?
Yes.
Can they do that? So I hope you also are like a little more convinced about that. And we examined the internals of this k-means algorithm without getting into, but basically that's it. That's the algorithm. So you just have to, you can write it in any programming language, but that's simply the algorithm. And maybe you're also thinking about some of your own data or problems that I hope you do at some point, that if you can look for these clusters. And yeah, I think that should be my presentation.